Hello everyone, my name is Karan Baker, a PhD student with the Department of Mechanical and Industrial Engineering at LSU, and I work with Dr. Adrian Stein on robust time delay filter design for precision motion control with non-zero initial conditions. Before I show you how we design our time delay filter, I'll briefly go over the motivations for this project. So vibrations exist in many systems that we see in daily life, such as 3D printing or drone payloads. Many of those vibrations are caused by non-zero initial conditions, which I'll call self-excited vibrations. There are also exogenous forces that are generated from external forces on the payload or on a 3D printhead. There also exists uncertainties in our system regarding our natural frequency and damping ratio, which changes the overall structure of our filter. So the goal of this project is to minimize the vibration at the end of our rest-to-rest maneuver, and even considering non-zero initial conditions or those uncertainties in our system parameters. So the basis of this feature comes from positive casting, or POSICAST for short. This originated from Tolman and Smith, two electrical engineers from the University of Berkeley. The goal is to split the input signal into individual excitations to make a new command signal. As such, we'll see a staircase where a part of our signals begins at the start of the maneuver, and then we'll see the delayed response later. For a basic input shaper, we'll see half of our input signal occur at the beginning of the maneuver, and then the other half of our input signal appear at the latter end of the maneuver. So the top of our block diagram here shows the original input signal, and the bottom of our block diagram shows a delayed signal. If we superimpose to get the structure in the center, the staircase structure, we'll get a time response that has minimal vibrations in our time response. So that's where time delay filters come in. If we take what we learned from POSICAST and we set up our split inputs again, we can apply a time delay filter very easily into an open loop configuration. We'll be able to introduce zeros that will cancel out the poles of our system. So this is a diagram of how we apply our time delay filter to our plant. And because it's in an open loop configuration, it is very easy to set up based on our input. So then I'll go over how we design a non-robust input shaper for a second order system. I'll explain how non-robust comes in compared to our robust later. So let's assume a second order model that's underdamped. This is applicable for our spring mass model, which is extremely simple to showcase. If we convert our second order model to the Laplace domain and assume our non-zero initial conditions, we'll get the formula shown here. We'll be able to isolate excess, so this will make it easier to input our time delay filter. So speaking of our TDF, here's the structure of our time delay filter. Because we're applying this to a unit step, we'll be multiplying by 1 over s in the Laplace domain. And because we need to assume unity gain, because our input signal needs to come back to a magnitude of 1, A0 and A1 should equal to 1. And because we're assuming that this is an underdamped case, we'll be applying an underdamped pole and inputting this into S. Applying our time delay filter to our input, we get the formula shown up here. And because we have both imaginary and real components, we can split this equation into the real component shown here and our imaginary component shown here. And then we have our third equation, which is our unity gain. Now we have 3 equations for 3 unknowns. OK, so now I'll go over a non-robust input shaper for a gantry crane model. So for the gantry crane model, we're going to assume that it's going to be a second order system without damping, and we want to achieve 0 velocity at the end of that maneuver. So this is our model without damping, and this is this model in the Laplace domain. When applying our TDF to our gantry crane model, we'll express it through our velocity input as shown at the top here. Because this is a velocity-driven input, we'll consider that our switch-off time is the displacement of our trolley divided by the maximum velocity of said trolley. And because this is a velocity input, we'll be considering SXI being equal to our filter multiplied by a step input. When applying this TDF, we can solve for our input in the Laplace domain, and we will apply our undamped poles S equals J omega n. So again, we'll apply our time delay filter to the original system, and we'll attempt to solve for our gains in our delay time. Here is our real component, and here is our imaginary component, both also set equal to 0. And once again, we'll have unity gain for A0 plus A1 equals 1. So applying a trig identity to split up that cosine of t plus Tp, and also using our unity equation to eliminate A0 from our real and imaginary components, we'll get this for our real, and we'll get this for our imaginary. So now we can solve for A1 using the imaginary component, and then we can plug that A1 back into our real component, which gives us this form. And this is alpha for the equation at the top. So now that we have alpha in this form, we can apply Weierstrass substitution or the tangent half angle substitution. So we can assume our alpha is of this tangent half angle form, and we can solve for alpha, which gives us our solution, two solutions here, a trivial solution and a non-trivial solution. Solving for our time gives us our solution here, and n is any positive integer. Now I'll explain our robust input shaper for the gantry crane. Considering a robust TDF, we will add a second time delay as shown in the equation at the top. Now, because we have 5 unknowns, and we'll need 5 equations to solve for those unknowns. So we'll consider the derivative of xs as shown here. And again, unity gain will be our 5th equation. So I'll show you our simulation results for both the second order model and the gantry crane for both non-robust and robust. And we'll also consider an uncertainty case. For our simulation results for the robust solution, we used Casati. For our second order system, we'll assume a damping ratio of 0.1 and a natural frequency of 2 pi. We will also consider initial conditions 0.5 and 0.1 for position and velocity respectively. Solving for our gains in our delay time results in A0 equals 0.84, A1 equal 0.2116, and T equals 0.97 seconds. As you can see from the graphs here, our position ends up at a position of 1, and our velocity ends up at 0 millimeters per second. For the simulation results of our gantry crane and payload, we will have a maximum velocity of 240 millimeters per second, and we will have a final displacement of 600 millimeters for our trolley. We will also consider initial conditions of 100 millimeters and 20 millimeters per second for our position and velocity, respectively. Our natural frequency will be pi, and solving for our gains and delay time, we have A0 equals 0.23, A1 equals 0.77, and T equals 1.707 seconds. For this specific simulation result, we applied the Weierstrass substitution that we showed earlier. This is an illustration of our simulation results for our gantry crane. As you can see, we reach a final payload position of 600 millimeters, and our payload velocity is near 0 at the end of the maneuver. Considering the robust case for our gantry crane, we'll have our initial conditions at 25 millimeters and 4 millimeters per second for our position and velocity respectively. Solving for our gains here are 0.4288 for A0, A1 equals 0.4236, and A2 equals 0.1476. Our delay times are T1 equals 1.245 seconds and T2 as 4.3969 seconds. So showing our non-robust and our robust TDF together on the left, while we have the trade-off of increasing the amount of time of the maneuver for our robust TDF, we do get closer to a 0 velocity for the robust TDF. Now, considering the uncertainty case, we're going to add 5% perturbation to the natural frequency. So the natural frequency will range between 0.95 pi and 1.05 pi with 100 equally spaced samples. We'll consider the same initial conditions of 25 millimeters and 4 millimeters per second. When comparing our non-robust TDF to our robust TDF, while it does take longer for our robust TDF to converge, we can show that the standard deviation for our position and velocity is lower for our robust TDF compared to the non-robust TDF at the end of the maneuver. We can show this numerically where the position standard deviation is 1.02 for our robust, while it's higher at 1.83 for our non-robust. And for our velocity, it is way smaller for our robust at 4.15 millimeters per second compared to 18.83 millimeters per second. And to consider that the residual energy of our system, which is shown in the form at the top here, we were able to, so we can show that our robust TDF noticeably reduces our residual energy compared to our non-robust TDF, even if our natural frequency is relatively uncertain. So as you can see here, at a no natural frequency pi, of course our residual energy will be considered near negligible. But as we increase the uncertainty of our natural frequency, that residual energy rises. But our robust TDF is able to consider that and noticeably reduce it compared to the non-robust. We will consider deriving closed form expressions for the robust TDF compared to just using the Casati solution, and we will further the study with an experimental setup for our gantry crane. And then we'll also consider a sensitivity analysis for the different system parameters for the gantry crane with respect to increasing the delays. As shown from our research, the robust TDF proved more effective for uncertain system parameters and reducing our residual energy and improving our maneuver. I'd like to thank Dr. Stein at LSU. I'd also like to thank CCTA for sponsoring this event and for Weston Gaslight and Concordia Hotel for hosting the event.